All right, these are the notes for 6.1. 6.1 is talking about growth and decay functions. Now, growth and decay functions have a distinctive look to them. You can't see these very well, but here, this is what an exponential growth function looks like. So it sweeps up like that. It gets closer and closer to the x-axis without touching it. So the x-axis is called a horizontal asymptote because it gets closer and closer and closer. That's a growth function, so it has positive slope. Here is an exponential decay function. It has negative slope. It still has here, this one has the x-axis for an asymptote again. When you look at the equation, it looks like this, y equals ab to the x. We'll have different equations, but this is the basic one. Now, a is the initial value. So if it asks for the initial value, that's what a is. B is called the growth or decay factor. Now on these, A is always a number, it can't be 0. B is always positive, and it can't be 1. So this base is always positive. So if A is greater than 0, so here if A is positive and B is greater than 1, then it's an exponential growth. So what you want to really do is look at B. If B is greater than 1, it's a growth function, so it looks like this one. If B is between 0 and 1, then it's a decay function, so it looks like this one. So if this number here is a whole number, 2, 5, 6, 4.2, whatever, it's exponential growth. If this is a decimal less than 1, like 0.8, or a fraction like 3/4 or anything like that, then it's a decay function. Notice the domain here is all real numbers because it just keeps going. These into the range is greater than 0 because we get all positive values on these. Right? So one of the first things you do is you look and say, okay, is this a growth or decay? So like this, and notice the base is 2. Well, 2 is greater than 1, so this is a growth function. It's pretty easy to graph these. You can just plug in a few numbers. Usually 0 is a good one, like because 2 to the 0, and almost anything to the 0 is 1. So 0, 1. 0, 1 will be a point on a lot of these graphs. Then what if x is 1? Well, that means 2 to the first, which is 2. So 1, 2. If x is 2, that'll be 2 squared. 2 squared is 4, so the point 2, 4. We kind of get the idea there. If we plug in negative numbers for x, like negative 1, that makes it 2 to the negative 1. Now here you have to remember, a negative exponent means take the reciprocal. So 2 to the negative 1 means the reciprocal of 2, or 1 over 2. So at negative 1, we're up at 1 over 2. If we did one more, like negative 2, that'd be 2 to the negative 2. Again, the negative exponent means the reciprocal of 2 squared. So at negative 2, the reciprocal of 2 squared is 1 over 4. So there's our graph. Again, it gets closer and closer to the x-axis without touching it. One like this, here notice the growth factor, or the b, is the base is 1/3. Well, 1/3 is between 1 and 0, so this is decay. So we know what its shape's going to be like. We can still plug in numbers. If we put an exponent of 0, 1/3 to the 0 is 1. Again, almost anything to the 0 power is 1. The only thing that's not is 0 to the 0 power is undefined. You could check that out by doing it on your calculator. That gives us 1 point. Now, if we get a few more, like if x is 1, well, 1/3 to the first is just 1/3. If x was 2, that'd be 1/3 squared, which would be 1 squared over 3 squared, so 1/9. Now, if x is a negative 1, remember, if the exponent's negative, that means it's the reciprocal. Well, the reciprocal of 1/3, if you flip it over, is 3. So 1/3 to the negative 1 is 3. So if I let x be negative 1, y is 3. If x was negative 2, that would be 1/3 squared, which is 1/9, and then the reciprocal would be 9 over 1. So that graph is going to look something like that. Or this one, here our base is 7/2. Now when you first look at that, you might see a fraction and say, oh, decay, but notice that fraction is greater than 1. So 7/2 is greater than 1. So this one is growth. And if we put in 0, 7/2 to the 0 is 1. If we put in 1, it's just 7/2, which is 3.5. If we would put in 2, that'd be 7/2 squared, which would be 7 squared over 2 squared, 49/4. So that's a little over 12, so we know it's going way up there. If we plug in a -1, again, that means take the reciprocal. Well, the reciprocal of 7/2 is 2 over 7. So at -1, we're at 2/7. If we did -2, that would mean you'd square it and get 49/4, and the reciprocal will be 4 over 49. So in general, we're getting a graph that looks like this. This last one here, notice here the base is 0.8. And 0.8, that's between 1 and 0. So this one is decay. So if we plug in 0, 0.8 to the 0 is still 1. If I plug in 1, I get 0.8. If I plug in 2, if you took 0.8 and squared it, you get 0.64. If I plugged in -1, if you think of 8 as 8/10, if x is -1, if you take the reciprocal, that'd be 10 over 8. So at -1, we're just, what about 1, not even 1 1/4. If we plugged in 2, that'd be 8/10 squared, which would be 64 over 100. Now you take the reciprocal, that's 100 over 64. So it doesn't go up very much there. So this graph looks something like this. All right, that's how you graph them. Now let's look at this first sample problem here. Tell whether a car Y, the value of the car is Y, and that's in thousands. So if it says it's 3, that's $3,000. Now they give you a model. That value can be approximated by this, where T, that exponent T, is the number of years since the car was new. So this is a way to plot is what happens to the value of your car over time. Well, it depreciates. Depreciation, one of the ways to do depreciation with exponential functions. So here, the first question says, tell whether that represents exponential growth or exponential decay. Well, here our base is 0.85. So 0.85 is between 1 and 0. So this is decay, which makes sense because wouldn't you expect the value of the car to go down as it gets older until it gets to like antique status? One other thing I kind of threw in here, what is the original price of the car? Remember I said this A that's in front is the initial value? Well, this is A right here is 25. So that means the initial price of the car is $25,000. So that number out front, that's the initial value. Now, before we answer the next one, and there's a mistake, I want to correct this on your sheet. I have a typo here. See on this form, here's the thing where it's called an exponential growth and decay model. It looks just like what we did, except 1 plus R is now equal to B. Except I made a mistake here. Notice it's got a T inside the parentheses. That T should be on the outside, not on the inside. So it should be Y equals A, then in parentheses 1 plus R, and then there's a T as an exponent outside. Same way here. That T should not be in there. It should be outside the parentheses. Now in this one, A is still the initial value. Now since B is 1 plus R, they use this format to put in a percent. Like let's say if R was 4%. If this is a growth formula, we take 1 plus 0.04, you'd get 1.04, that's the B. If it's a decay, you take 1 minus whatever that number is. Like let's say it was a decay of 4%, it'd be 1 minus 0.04, or 0.96. So that's how from the equation you can find what is the rate of growth. So going back to this one we were just talking about, notice the base was 0.85. Well, if I take 1 minus 0.85, that's 0.15. So that's our percent as a decimal. So this would be a 15%, and since our base was 0.85, decrease. So that's the annual rate of decrease of that. When will the value of the car be 8,000? This one you want to do with your calculator, and you can use it's fine with the graphing calculator. That Desmos calculator that's on that the link is on your Canvas page works great for this, almost easier than this. What you want to do is first we want to put that equation in our calculator. So y equals 25 times 0.85, and the exponent key is this one right here. That's the exponent key. So I hit that exponent, and now I want to the x, so I'm going to hit the xt theta. Anytime you want the variable, you use the xt theta button. So it looks like that. So 25 times 0.85 to the x. Now we're going to graph that. Now if I go to graph that, you never know, it may not show up very good on your graph. It may be off the graph, like here there's just a little piece. You can try this. You could try hitting zoom and then 0. So a good way to do this is, put the note up here, is zoom 0. That's called zoom fit. So it'll try to fit, your calculator will try to fit as much of the graph as possible into the screen. That's what that's for. That can be kind of handy on these. Well, now I want to find out when that reaches 8,000. Well, we're in thousands, so we're looking for 8. So I'm going to hit the trace button. So you hit trace. Now, if you look at your y values, like here it's 25, 0, 25. Well, that's what we said before. At time 0, when you first bought the car, it's valued 25,000. Now, if we use our arrow keys, we're going to just keep going to the right and watch your y values. We want to find out when they're approximately 8. So if you look at the y values here, I'm 8.55, 8.26, 7.98. So we're a little past 8. Well, that's pretty close to 8, 7.98. Well, it says my x value is 7, 7.02. So that's approximately 7 years. That's how you do it on there. See if I can, I don't use this Desmos calculator much, but see if I can show you on the Desmos calculator. Say it's almost easier on the Desmos calculator. So on the Desmos calculator, we're going to enter that in. So we'll see this. So if we enter in that same one, so y equals, see that again. So we have in there y equals, now I need, what, 25. So 25 parentheses. Now my base was 0.85. I'm going to hit the button right here. You can't see it. There's a button here that says A to the B. See right here where it says A to the B. I'm going to hit that. That puts my exponent on there. I want an X there, so I'm going to put X. So there's my equation in there. Now, if we look at our graph over here, we want to trace that. Well, the easy way to trace here is you just put your finger on the graph. You see the numbers over there? Just move this over. You see the numbers out there to the right side? They're kind of faint here. Those are my values. So I'm going to watch those until I get to where the y value is about 8. That's somewhere right in there. So it looks like about 7 years again. So that's how you do it on a Desmos calculator. Get real easy. Okay? page turned yellow. Anyway, so that takes care of that one. Next one, write an exponential model. So we're going to take this information and put it into that model. Well, let's see. So we're plugging into that. This looks like it goes up 1.18, so this is a growth. So we're plugging into y equals a times 1 plus r to the t. That's what we're plugging into. So y equals a. Well, a is the initial amount. That's 6.09 billion. I'm going to just leave it as 6.09 and remember that it's in billions when I get done. Now for 1 plus r, that'd be 1 plus. Well, it's our rate of growth is 1.18%. As a decimal, that's 0.0118. And all that's to the t. That's what we have there. Now we can combine those inside the parentheses and just make that 1.0118 to the t. There's our equation. It says write an exponential growth model. There it is right there. Now it says estimate the world population in 2005. I'm going to go back to my calculator and enter that into my calculator. This time under y equals, well, I guess we did that before under y equals. So I'm going to put in there 6.09 times 1.0118 and then hit my exponent key. And that is to the x there. And graph that. And I hit zoom 0. Could have hit zoom 6 first, or maybe it would have been okay. And there. So there's a graph of that. Now it says estimate the world population in 2005. So press trace up on the top, and then just press. We started measuring in 2000, so 2005 would be 5 years later. So I'm going to hit 5 in my trace. And notice now I get 6.45789. So if I round that off to a couple of decimal places, that's 6.46 billion people. So you did that by plugging in 5 because it's year 5 from 2000. This last part, estimate the year when the population was 7 billion. Let's go back to our calculator. Now we're going to watch the y values. We want to know when they reach 7. So if I use my arrow key and keep going to the right, it looks like I'm getting pretty close. So there I'm at 11.7, I'm at 6.986. At 11.9, I'm 7.00357. So you could realistically use either one. I think the second one I saw closer, that was 11.9. So it's 11.9 years, or approximately 12 years. Now it says estimate the year where we started in 2000. If I go 12 years later, that's 2012. All right, one more. Now this last one uses a little different equation. I forgot to put this in your notes, but this is for something called compound interest. Compound interest formula looks like this. A equals P times 1 plus R to the n. Let me start over. I shouldn't have that big parenthesis start off with. So we have A equals P times 1 plus R over n. And then outside the parentheses, my exponent is n times t. So that's the compound interest formula. Now in that, A represents the final amount. So if you have money invested, that's how much you end up with. If you're borrowing money, that's how much you borrowed. P is called the principal. The principal is the initial amount. So it's how much you borrowed or how much you invested. Then R is the interest rate, and it's always as a decimal. Then here there's two N's. N is the number of times compounded per year. So that means if you say it's semi-annual, N is 2 for twice a year. If they say it's monthly, N is 12 for 12 months in a year. Daily is 365 days per year. That just tells you the money to substitute in. So if we use that formula, here T is in time. That's normally in years, but it could be whatever the problem says. Now, here we've got a formula that says you plug in $9,000, they tell you the interest rate, tell you 3 years, and it's compounded quarterly. Let's substitute in that equation. So our final amount equals our principal. Our principal is how much we started with. Well, we started with a $9,000 deposit. Okay. So there's our final amount equals our initial amount, which is 9,000 times 1 plus R. Well, here it says the annual interest is 1.0 or 1.46. So that's 0.0146 as a decimal. And on the bottom is N, the number of times compounded per year, where that's quarterly. Quarterly means 4 times per year. Then in the exponent, we have N times T. Well, N, we already said, was, I'm just going to write this somewhere. So N is 4. We already have N is 4. I'm sorry, I lost track. What is it? Up in the exponent, we have N again. So 4 times our time, which is 3 years. So the equation should look like that. Well, we just worked that out on a calculator. So you can take 9,000 times 1 plus 0.0146 divided by 4. And the exponent here is 4 times 3, which is 12. So I'm going to find all that, and then I'm going to hit my exponent key and hit 12. Let's see what I come up with there. Looks like I got, if you can read that, I can't read it very good. 6.02 something. Something I did wrong there. I don't know what. Oh. Yeah, I didn't do that one right. I'm going to start with what's in here. 1 plus 0.0146 divided by 4. I'm going to take that to the 12th power and take that times 9,000. Get 9,402. That's more like it. So that means at the end of 3 years, I started with 9,000. Now I have 3 years. I have $9,402.21. All right, everybody see that okay? So I did this first on my calculator, 1 plus all of that, and hit enter. Then I hit my exponent key, and then I hit 12, because 4 times 3 is 12, and I hit enter. And I took that whole answer times 9,000. That's where I got the 9402.21. And that should do it for 6.1.